Hi, today we're going to finish chapter one. And I did want to announce that on Thursday, we're going to have our second bonus quiz worth 2 points. And it's going to be on Thursday, September 3rd. And it'll cover topics in chapter one that we've covered up to this point. Today, we're going to finish this chapter in a first part video dealing with the mole concept. And we're going to define the mole is simply nothing more than a counting number. And we'll go over and review some counting numbers we may recall just from our practical normal life experiences so we can understand a little bit better about what the mole is. So let's review a little bit and discuss some topics that we've discussed already. So in our prior lecture, we've discussed the atomic mass unit. We refer to this as the AMU. The atomic mass unit is used to report the mass of single atoms. And as a reference, one atomic mass unit is 1/12 the mass of the carbon-12 isotope, which is roughly 1.66 times 10 to the negative 24th grams. Now, the atomic mass unit is convenient because now we can discuss a unit that's a little easier to relay to our colleagues and so forth or other students, but it's not practical. And when I say it's not practical because we don't go into the laboratory and weigh out atomic mass units. We measure in the macroscopic world particles that we have large amounts of, and we usually weigh these out in masses of grams, kilograms, milligrams, and so forth. In other words, when we go into the laboratory, we don't have some way of measuring single atoms. We can't do that in any of the larger universities. We can't measure single atoms. So what we need to define a way to measure out large numbers of particles that we can apply to real world samples. Because if we think about a real world sample, let's just think about a teaspoon of water. If we take a teaspoon of water, if we could go in there and count them, we're going to end up with about 2 times 10 to the 23rd water particles or water molecules. So what we need to do is we need to utilize a counting number that gives us a number of particles that we consistently weigh out, and that'll tell us a little bit more about the masses of our samples that we're dealing with in the laboratory setting. And we'll learn more about mass relationships when we discuss balanced chemical equations. But for now, we need a counting number. We need some large number of particles that we can always use in our applications to tell us a little bit something about how one atom, in terms of one particular element, is compared in mass to another atom of a particular element. So we need a counting number. Can you think of some counting numbers? Counting numbers. One that we might be familiar with, a dozen. So 1 dozen, if you go to Dunkin' Donuts or donut shop, a dozen donuts tells us that we have 12 donuts. We can buy a dozen baseballs. We'd have 12 baseballs. A pair is another counting number. Normally, we buy a pair of shoes, and those are 2 shoes. One other type of counting number is the gross. 1 gross is equal to 144 items. So each of these definitions that we have are counting numbers, and they just simply represent a particular number of items that we might be dealt with in a real life setting. A dozen is 12 items, a pair is 2 items. 1 gross is 144 items. In science, to measure small particles such as the water molecule on a macroscopic scale, we need a heck of a lot more than a pair, a heck of a lot more than a dozen, more than a gross even. We need a very large number of particles that we can measure out, and what we use is the mole. Let's define the mole. It's a counting number such as we just described. 1 mole consists of 6.022 times 10 to the 23rd items. Remember, a dozen is 12 items. A mole is 6.022 times 10 to the 23rd items. And it's an SI standard that we use for the number of particles that we're dealing with. And this is the SI standard for number of items, particles. We'll just say number of particles. And we define the mole in terms of an experimentally determined property. One mole, it's been determined experimentally. It's the number of atoms of carbon-12 isotopes in exactly 12 grams of that particular sample. So that's how we define the mole. It's the number of atoms of carbon-12 in exactly 12 grams of carbon-12. And the mole is sometimes referred to as Avogadro's number. And it's given to you on exams. Sometimes you'll see a reference NA, N, capital N with an uppercase A that's subscripted. Avogadro's number, as we said, is 6.022 times 10 to the 23rd items. So it's given on exam. Let's think about how big a mole is. Remember, we said 12 donuts or a dozen donuts, 12 pennies, a dozen pennies. What if we had a mole of pennies? That's a lot of pennies. If we lined up these pennies side by side, we have some information based upon the diameter of the penny. These would circle the Earth 300 trillion times. That's a lot of pennies, and it's a very large amount of particles or substances, anything. We can have a mole of anything. And we use it in science to give us samples that are on the macroscopic level that we can weigh out in terms of grams. And now we can compare a mole of one particular atom, perhaps carbon, with a mole of another particular type of atom, such as potassium. Now, what's important about the mole is its mass relationship and how we define the atomic mass unit. So let's think about this. Since we're defining the mole and the atomic mass unit based upon the carbon-12 isotope, we have an important relationship that we're going to be using a lot throughout the semester. Let's look at the periodic table symbol for carbon and this number that we've defined earlier as the average atomic mass. This is important. What this number tells us is that one atom of carbon has a mass in atomic mass units 12.011 AMU. What this also tells us is that if we have 1 mole of carbon atoms, they would have a mass, the same number. The only thing that's different is the unit. It's in grams. So this is a real important relationship. This number that we have in the periodic table, known as the average atomic mass, it tells us the mass in atomic mass units for one atom of that substance. If we had a mole of atoms of carbon, they would have a mass of 12.011 grams. Remember we said if we compared carbon and potassium, let's look at potassium on the periodic table. If we turned and looked at potassium on the periodic table, we would see that one atom of potassium has a mass of 39.10 AMU. If we had 1 mole of potassium, it would be 39.1 grams. So this number that we see on the periodic table, this is true for any element. This decimal number, the average atomic mass, that's the mass of one atom of that particular substance in atomic mass units, and it's identical to the numerical value for 1 mole. The only thing that's different is that's in grams. So this is true for any element on the periodic table. And what we're going to show a little bit later in our next video, part 2, is we're going to use this number to help us establish some problem-solving strategies for dealing with mass relationships and mole relationships for atoms that we're going to extend a little bit later. Thanks a lot, and we'll get back to you later today.